say let's do another quick example in which you have to, for example, differentiate a function, say, I don't know, e to the x, but e to the t dt, but this time you have to differentiate this from 0 to, say, sine x factor. Okay. So I have to, integrate or then compute the derivative of this integral with the limit of 0 to sine x. So you're going to do the same. Let's take u to be sine x. I know that du by dt is going to be the cosine x. This integral with this new notation is going to be d by dx of 0 to u e to the t dt, where I can do this, apply chain rule, du by dx. This will become e to the t, okay, by the identity that I mentioned, and not e to the t, not e to the u actually, times, no matter what limit we have, doesn't matter. Du by dx is what do you call cosine x, and on the place of u you can also substitute what do you call sine x. So this is what is really the derivative of this function. Okay. You can ask a question also that, okay, what if I have a function that is in lower limit actually, x to, I don't know, x to 3 actually, and I have to do e to the x dx or e to the t dt. So what are you going to do? Then we know about basically integral. So we talked about this property last time, that if you wish you can flip basically the limits as well. So if you're going to flip the limit, what are you going to get? Minus 3 to x and e to t and dt. And then you know that how to solve this integral. Okay, so you can easily do such problems as well. But the more interesting question would be, what if the both of the limits are variable? In other words, you have to integrate, say, e to the t dt from the x up to, say, x squared. Okay? So before revealing the strategy or the answer to such question, I would like to leave this for your, what do you call, understanding. I'm leaving this for your reflection, that can you figure out some way of computing, such integrals? And the hint is, I mean, you can develop the formula, but you can also do it without developing the formula as well actually, by using some of the basic properties of the integral, the definite integral. Okay. By the way, this observation that I have just wrote are this key theorem in this set of discussion, the discussion that we had so far. So this theorem is called I call it a second fundamental theorem of calculus. The previous theorem is first fundamental theorem of calculus. So it's called the second fundamental, okay, theorem of calculus. Okay. So you can see that fundamental theorem of calculus and second fundamental theorem of calculus, these are really the bridges between the differential calculus and the integral calculus. It links them, it puts them together. So if I just write the statement of it, I'm going to say that suppose f is continuous on an interval a to b, okay, then if g of x is a function that is the integral from a to x of say f of t dt, then g prime of x is really the integrand actually f of x. Okay, and this is true for any x in the interval a to b. This is the statement of second fundamental theorem of calculus, and there will be several interesting exercises for you in which you have to solve such exercises. You have to solve such exercises. And as I said, think about this problem as well. That if you have to solve it, I know how to deal with it. That okay, you know, if the integral starts from a constant and ends to a variable or a function, I know how to derivate such integrals. Or if it starts from a variable and ends at some constant, I know how to deal that situation. But if it starts from one variable function to another variable function, okay, then how to integrate it? The answer is that try to express this in the terms of this integral and say such integral. Try to compute them, or break such kind of integral in the form of this kind of integral actually, x to a, something like that, in which one limit is constant and another is variable actually. Anyway, so there are some exercises in which such hints are given. Maybe you can also think and learn from those exercises and hints as well. So I hope we have so far understood through different examples and several examples the notion of definite integral and indefinite integral, what they mean, what is their interpretation, how to compute them basically, and how to compute them for easy integrands actually, or simple integrands, in which it is possible to directly deduce the antiderivative of the function. So I hope we have understood it. Now we will like to really move towards the area in which we're gonna learn the different kind of integration techniques. Okay, integration techniques. Okay, that if you have been given, this kind of, for example, list of integrals, you know how to integrate them directly. But if you have an integral of a form which does not follow any of these forms actually, then how to integrate those kind of functions actually. Okay? The answer is then you have to always, try to convert them into the one of such forms. So if there is an integral which is not in any of such forms, then we will try to convert them in the terms of any of such form actually, and then apply what do you call one of the techniques. So let's, for example, do some examples, and let's start with, say, a very first technique of integration. Okay, it's called the substitution technique, the elementary technique, the most useful technique actually. Okay. Substitution technique. Okay, substitution technique. Where does the substitution technique would work? See, if I have to, for example, integrate e power x dx, I know how to integrate it. Okay? That the answer is going to be e to the x plus c. Okay? The antiderivative is simple. If it is, say, 2 times of e to the x, it's easy to still deal with. That the outcome of this is going to be 2e to the x plus constant. If I add 2 into the e to the x, this is still easy to deal with actually, because this follows this form actually, that if you have two functions added together and you want to integrate them, what you can do, integrate them separately and sum them. So the integral of a sum is the sum of integral. Okay, so I know how to deal with such kind of integral as well. If I have 2 plus e to the x, I know how to solve it actually. So the outcome is going to be, I know the integral of the antiderivative of 2 is 2x and e to the x is e to the x plus constant c. But the interesting situation would be, what if instead of having 2 here, I have a say 2x here dx. And as for what should be the antiderivative of this? Or say instead of having this, I have say e to the 2x plus 3, a linear expression in the power. How to integrate it? I know how to integrate, for example, sine x dx. But the question is, how to integrate, say, sine instead of x if I replace this by a function of x? Say 2x plus 3 dx. Imagine I know that how to integrate, say, 1 over x. I know it's going to be log of absolute of x plus c. But what would be the integral of, say, if I do the 2x plus 3, for example? Okay. So I just in all of these examples, what I'm trying to say that in this standard table, of integrals, wherever you have x, if I replace this, for example, by a linear expression, say 2x plus 3 power n, or e to the 2x plus 3, or sine 2x plus 3, or secant square 2x plus 3, okay, or 1 over 2x plus 3 square plus 1, or a to the power 2x plus 3, So in all such situations, if by x I replace what you call a linear expression, okay, then how to deal with such situation? Okay, how to deal with such kind of situation? What if I have 3? I know how to integrate 3 power x, but how to integrate 3 power 2x plus 3 dx? Okay. So what I want really, by writing all these examples, what I want is that try to see the close relationship between these functions and the list of the functions that you have here. So what is the difference between these functions and the functions that you have here? Okay. The major difference is that here, wherever you have x, you are replacing x by a linear expression. Okay, replacing them by a linear expression. The question is how to integrate such kind of function. I know, how to integrate square root of x dx. It's not difficult because I know that I can write this as x power 1/2. But the question is, how can I integrate 2x plus 3 and dx? Okay. And answer to all these questions problems is that try to convert this into such form. Okay. This into form of 3 plus x, 3 power x dx. This into such form. This into such form. Okay, this into the form of e to the x and dx. So how to do it? The answer is really easy. I have started with linear expression where wherever x by x I have replaced 2x plus 3. So the answer is do the substitution. So now let's solve one particular problem based on this observation of substitution activity. So imagine I have this e to the 2x plus 3 dx, this indefinite integral. I can't directly guess what would be the antiderivative of this function. I mean, if you can write it directly. But as such functions are going to be a bit complicated, direct guess would not work actually. So you have to try to convert them into the one of the standard form. So how are you going to do it? So you're going to set this expression 2x plus 3, give it a name t or u or whatever you like. Then I have also tried to change what do you call this differential. Okay. So the dt by dx is going to be 2. Okay, dt by dx is going to be 2. So I can say that my dt becomes 2 dx. Okay, though this is a bit misleading way of writing, but okay, for the sake of computation it's okay. Or you can say that dt divided by 2 will become, what do you call, 2x. Okay, so if the ratio of dt by dx is 2, then dt by 2 is going to be dx. Why this is a bit misleading? Because these dt's are not concrete numbers actually. They are infinitesimal quantities. Okay, what are these? Who knows? Okay, so they are tiny quantities. Anyway, but for the sake of computation, we can do this. So we have now expression. I can convert this into the t. I have also an expression to convert my differential into the in the terms of the differential of t. So if I now reshape this function, so this will become e to the t, and this dx will become dt by 2. So this is going to be dt, okay, divided by 2. Let's put 2 here actually. And now integrated. So how are you going to integrate it? So now this has came in the form of, what do you call, one of the standard forms. Okay. Which two standard forms? For example, one property is that, okay, you have a constant multiplied by the function, so you can pull that constant out and integrate. So I can take that 1/2 outside of integral, and what is going to remain inside is e to the t. And what is the integral of e to the t, or antiderivative of e to the t? So it's e to the t plus c. So I took 1/2 outside, then what is remain is e to the t dt, and you have 1/t, e to the antiderivative of e to the t is e to the t plus c. So is this kind? The answer is no. The problem was involved in the terms of the variable x, so the answer should also be involved in the terms of the variable x. So what you're going to do, replace wherever you have t, just replace by tx plus 1. So this t is like a dummy variable. Okay, so you have kept it for some moments, and now you are returning it back. So when you're going to replace this back, you're going to get e to the 2x plus 3. E to the 2x plus 3. Okay. How about instead of having e to the x, say I have sine x actually. Maybe I have, say, cosine of 2x plus 3. dx. What kind of technique would you're going to say? You're going to do the same solution. Let's take t to be 2x plus 3. By the same technique, dt by 2 will become dx. So if you make these two substitutions here, so the integrand will become cos t, and this will become dt divided by 2, and then I can pull 1 over 2 out. The integral of cosine t, the antiderivative of the cosine t is sine t plus constant, okay, and so I can replace t by 2x plus 3. 2x plus 3, okay. Sine 2x plus 3. So here is an interesting observation. Okay. What if I have some function, any function, okay? So for example, I have some function f of x dx, and I know that the integral of this function is, the antiderivative of this function is this capital f of x plus c. And this function is any function. And I'm saying, now what would be the integral of, say, a plus some bx, or maybe ax plus b dx. Question is, what would be the outcome? So, in other words, you know, your f of x could be e to the x. So you're talking about e to the ax plus b. So if your f of x is sine x, sine ax plus b. If your f of x is, say, you know, cosecant square x. So this is cosecant square ax plus b. So in every single function, so this is like generalizing all these functions. In every single function, okay, if by x I replace a linear expression ax plus b, then what would be the output? Okay, what would be the output? You can make the same. So I can make a substitution. Say let t is, say, ax plus b, and dt is over dx is going to be what? B, the derivative of b is going to be 0, derivative of x is going to be 1, so it's going to be a. Hence, by the same, I can say that dt by a is going to be dx. Okay, I'm saying again and again, this is just for the computation purpose actually. So what your integrand will become? So your integrand will become f of, what do you call it, t, and dx will become dt divided by a, where a is the coefficient of x. Okay, a is the coefficient of x. So what would be the integral of it? So pull out this 1 over a. The integral of, so this, so if you take 1 over a outside, so it takes this form. On this form I can apply what we call antiderivative formula. So it's going to be 1 over f of t plus, what do you call, see, where f is the antiderivative of small f. So this will become 1 over a, and now on the place of t you can replace ax plus b plus c. Okay, so this will become 1 over a f of ax plus b plus c. So what does it mean? If you have a function f whose antiderivative is capital F, and in that function you have ax plus b involved, then what you need to do, directly compute the antiderivative of f, substitute ax plus b into it, and divide by the coefficient of x. Okay? So divide by the coefficient of x. So you can apply this trick to solve, for example, any kind of standard problem. So if I, for example, say that what would be the integral of 3 plus minus x plus 2 dx, I'm going to say, okay, what is the antiderivative of 3 power t? So the antiderivative of 3 power t is really 3 power t over log 3. 3 power t over log 3. So that's the antiderivative of it. So what would be the antiderivative of this expression? So by this, take the antiderivative, which is 3 over log 3, and in the place of t substitute ax plus b, which is minus x plus 2, and divide everything by whatever is the coefficient of x actually. Okay? So in other words, multiply by minus 1. So you're going to get minus